My name is Dan Cantrell and I work for Clark PUD. I'm a storekeeper here, work in the warehouse. And today what we'll be doing is talking about current electricity. We're going to talk about insulators, conductors, AC and DC voltage. We're going to go over the Jacob's ladder and we're going to do a Tesla coil. Current is the flow of electrons. Current is 1 amp. It's also known as 1 coulomb, or 6.24 times 10 to the 18th power, or 6.24 billion. Almost the speed of light. That's how fast it travels. So current moves through wires or conductors. And a conductor is something that allows the free flow of electrons. It doesn't like to stop it. An example would be this copper wire. This copper wire is a really good conductor. It allows those electrons to flow without any points to stop. So what we want is the current to flow through wires and not down poles or through houses. We want to stop that with an insulator. And what an insulator does is stops the flow. It does not allow it to go through. So here we deal with two kinds of electricity. We have AC, alternating current. We also have DC, which is direct current. And the differences are like they sound. AC, alternating, it's produced on the sine wave, up and down, up and down, up and down. Direct current is one line, it goes from negative to positive. It's the same voltage, nothing changes. Some examples of an alternating current is anything that you plug into the wall. The wall outlet is alternating current. DC current is something that you use to charge your cell phone, which is with the charger. And what happens is you plug this into the wall, it's alternating current. Inside are capacitors and resistors, and they change that to direct current. It enables you to charge your cell phone. A battery like this is a direct current battery. It flows in one direction, from negative to positive. Alternating current goes up to the highest voltage, back to zero again, and it does this what they call a sine wave. An example of an AC would be your lights. One of my favorite pieces of equipment, I even have these at home, is what they call a Tesla coil. And remember earlier we talked about AC-DC. This is an AC to DC converter. And so what this does is takes 120 volts AC, converts it into thousands of volts DC. And when I plug this in and turn it on, what you'll see is a little blue spark coming out of here. And that's superheated air. The electrons are going away, kind of forming a form of plasma. And at this point, you can either play music with it, with the frequencies, if you change the frequencies a little bit. What I'm gonna do is show you how the electrons in the air that are all excited and moving around will actually light a light bulb without anything being touched to it. So as I bring this light closer, I'm going to excite those electrons, and inside that bulb these electrons are getting really excited and start bouncing off each other. And you can see how bright it is when I get really close, but as I pull it farther away it gets dimmer. There's more airspace in there, more insulation, because air is kind of an insulator. So like the Tesla coil, I'm going to show you one of my favorite pieces of equipment we have here. It's called the Jacob's ladder. And what the Jacob's ladder does is gives you a good example visually, and if you were close enough you could hear it, of how electrons move. And if you can see the two wires going up, one is connected to a power source and the other one is connected to the ground. And if you look closely, they're not touching. Now remember, air is a form of an insulator. The drier the air, the better the insulator. The more humid the air, the less of an insulator. What we're going to demonstrate is how this works. So behind here and behind all this stuff is a 120 adapter, and what it does is a step-up transformer. And what a step-up transformer does is steps up the voltage. We're going from 120 volts to some of these work at 50,000, 60,000 volts. This one I think is around 8,000 volts. And so what it's doing is when I push this foot pedal down here to demonstrate, it's going to create an electric charge. And what's going to happen is the gap on the bottom of that wire is really close, and that electric charge is going to be able to jump to the ground, which what you'll see is the ionizing of the air, which is the burning of the air. And the reason it goes up is because hot air, it rises. as it gets wider, the gap gets wider and wider, and at some point the ionized air is not enough to keep the circuit going, and that's why it goes out. So I'm going to demonstrate that by pushing the pedal.